This is video 2 of topic 10 on groundwater hydrology. In this video we'll talk about Darcy's law. Darcy's law is a basic equation governing groundwater flow that was first developed by the French hydraulic engineer Henri Darcy in 1856. Based on lab experiments using sand filters, Darcy concluded that the flow rate Q is proportional to the cross-sectional area of the sand filter times the hydraulic gradient, or dH by dL. This gives us the equation Q is equal to K times A times dH by dL, where Q is the flow rate in cubic meters per day, K is the hydraulic conductivity, which is a function of the material through which the flow occurs, A is the cross-sectional area in square meters, and dH by dL is the hydraulic gradient. Darcy's law is more formally known as Darcy's law for flow through porous media. It assumes linearity between the flow rate and the hydraulic gradient. This is valid in most but not all cases, which we'll discuss in a second. This was Darcy's apparatus. He had a water tank, then he had a pipe, and there was a sand filter in that pipe. He had two piezometers. He measured the head difference between those two piezometers as well as the flow rate, and he knew, of course, this cross-sectional area. And from this information, he was able to derive the equation that the flow rate was a function of the property of the medium multiplied by the cross-sectional area multiplied by the hydraulic gradient. Now, the assumptions for Darcy's law break down when the flow is turbulent. This may occur in the immediate vicinity of a pumped well. It's also invalid for very fine-grained materials, and it should only be used when the medium is completely saturated. The flow also varies with temperature, which this equation does not include. Approximate values for the hydraulic conductivity K are given below for a number of different media. The conductivities can easily vary over several orders of magnitude for a given category of material, depending on the particle orientation and shape, and the relative amounts of silt and clay present in that medium. To give you an idea though, here are the materials: clay, sand, gravel, gravel and sand, sandstone, limestone and shale, quartzite and granite, their conductivity in imperial units, and then their conductivity in SI units. And you can see they vary really dramatically. So here's clay at 0.0004 meters per day, versus sand at 41 meters per day, and then gravel at 4,100 meters per day. So the material does matter. A few important definitions are here. The first is that homogeneous aquifers have the same hydraulic conductivity throughout them. Aquifers with the same conductivity in any flow direction are called isotropic. Heterogeneous aquifers have differing hydraulic conductivities from one place to another in the aquifer. The conductivity may also depend on the direction of flow, so it's common to have a higher conductivity K horizontally than vertically. Aquifers in which the conductivity depends on the flow direction are called anisotropic. And aquifers are rarely, if ever, both homogeneous and isotropic. Now, it can be important to estimate the flow rate of groundwater through an aquifer, in other words, the velocity. And here's an example of why. Let's imagine that we have a toxic plume that exists up gradient from a water supply well. We want to have some idea of how quickly that toxic plume is traveling towards our well. There are two different expressions for velocity. The first is called the Darcy velocity, and it's just based on the regular equation we learned back in Civ 330, which is that Q is equal to A times V, so that V is equal to Q over A is equal to K dH dL. The average linear velocity includes porosity, since fluid flows through the pore spaces and not the entire cross-sectional area, which includes the mineral grains. And so V prime is the symbol we use for the average linear velocity, and it's just the Darcy velocity V over eta, which we also often write as phi, and it's equal to K over eta dH dl. So again, we can often write that eta as phi instead, and really this v prime is a better representation of the velocity of groundwater flow than the Darcy velocity. So unless you're told otherwise, you should assume that you should use v prime if you're asked to calculate, say, the time of travel for a groundwater plume. The Darcy velocity is derived as follows. Knowing that q is equal to a times v, where q is the flow rate, a is the cross-sectional area, and v is the flow velocity, we can solve for the velocity with Darcy's law as v is equal to q over a is equal to ka dh by dl over a is equal to k dh dl. It's pretty simple. This velocity v is known as the Darcy velocity. Now, in terms of the Darcy velocity versus the average linear velocity, there is a shortcoming of the Darcy velocity, as I mentioned a few slides ago. The Darcy velocity assumes that the entire cross-section A is available for water flow. However, much of the cross-sectional area is made up of solids, so the area through which all the flow takes place is much smaller. Therefore, the real groundwater velocity is considerably faster than the Darcy velocity, and so we solve for a different velocity as we did on a previous slide. That's called the average linear velocity, or sometimes the seepage velocity. To find the value here, we're going to revise the cross-sectional area term A to A prime, which represents only the pore spaces in the aquifer material. Then V prime is the average linear velocity, and we can rewrite so we know that the flow rate is Q, which is equal to AV, but we also know that it's A prime times V prime. And if we solve for V prime and then insert an arbitrary length of aquifer of L, then V prime is equal to AV over A prime. This is from the previous slide. Here we insert our arbitrary length L so that we have a volume and another volume. This is the total volume through which the flow occurs. And then this is just the void area, the void volume. And so then we have the total volume times the Darcy velocity over the void volume. And since the void volume over the total volume is the porosity, eta, then the average linear velocity is just the Darcy velocity over the porosity. So V prime is then Darcy velocity over porosity, which is V over eta, or V over phi, and then we get this equation we've already seen. This ends video 2.